Welcome back, Focus Learners, to another explainer. Today, we're unpacking Chapter 1, A Square and a Cube. We are going to uncover the really fascinating mathematical patterns that basically govern the numbers all around us. We'll start with a centuries-old 100-locker puzzle that perfectly sets the stage for our journey into two-dimensional squares and three-dimensional cubes. We'll learn their secrets, figure out how to reverse engineer them, and finally, put all our brand new tools to the test. Let's get right into it.
So here's our roadmap for today. We'll kick things off with the locker puzzle mystery, then decode the secrets of square numbers and discover square roots. After that, we're adding a dimension by exploring perfect cubes and finding cube roots. We'll wrap it all up with figuring it out together, where we tackle every puzzle type from the chapter. Okay, let's dive straight into Section 1, the locker puzzle mystery. Imagine this scenario. Queen Ratnamanjari wants to leave her precious stones to her son, Koisnam, but she knows her 99 other relatives are going to completely pester him about it. So she designs a pretty brilliant puzzle. In a secret room, there are 100 closed lockers. She assigns each of her 100 relatives, including her son, a number from 1 to 100. Person 1 goes in and opens every single locker. Person 2 goes in and toggles every second locker, meaning they close it if it's open. Person 3 toggles every third locker, and so on, all the way up to person 100. At the very end, only the open lockers reveal the code to the safe.
Now, Koisnam actually figures this out before anyone even touches a single locker. How? Well, he realizes a locker is only toggled for every factor its number has. Take locker 6, for example. It's toggled by persons 1, 2, 3, and 6. Because it has an even number of factors, 4 of them, right, it ends up closed. The only way a locker stays open is if it gets toggled an odd number of times. And the only numbers in existence with an odd number of factors are perfect squares. Think 1, 4, 9, 16. The queen also left a clue that the passcode is the first 5 lockers touched exactly twice. And numbers with exactly 2 factors, just 1 and themselves, are prime numbers. So that brilliant 5-locker passcode, it's 2, 3, 5, 7, and 11.
That puzzle is literally the perfect introduction for Section 2, Secrets of Square Numbers.
And this right here brilliantly illustrates the hidden rules of squares. Just look at the perfect squares of 1 through 10. We've got 1, 4, 9, 16, 25, 36, 49, 64, 81, and 100. Look really closely at the digits in the units place. They only ever end in 0, 1, 4, 5, 6, or 9, never 2, 3, 7, or 8. Now, an ending of 6 doesn't automatically guarantee a square, like 26 isn't 1, but an ending of 2, 3, 7, or 8 guarantees it is absolutely not a square. Also, check out the number 100. It has 2 zeros. Perfect squares can only ever have an even number of trailing zeros, meaning a number with 3 zeros at the end will have a square with 6 zeros. Now, here's a pattern that feels almost like magic. Take consecutive square numbers and subtract them, and you get odd numbers. 4 minus 1 is 3. 9 minus 4 is 5, 16 minus 9 is 7. If we just reverse that logic, it means you can build consecutive square numbers simply by adding consecutive odd numbers starting from 1. 1 plus 3 is 4, which is 2 squared. 1 plus 3 plus 5 is 9, which is 3 squared. The sum of the first n odd numbers will always perfectly equal n squared.
We've built these squares up, so now let's move on to Section 3, Discovering Square Roots, where we do it all in reverse. Just like subtraction is the inverse of addition, the square root is the inverse operation of a square. But there is a catch we actually tend to forget. We all know 8 squared is 64, but negative 8 multiplied by negative 8 is also 64. So technically, every perfect square has 2 integral square roots, a positive and a negative one. For our purposes in this explainer, though, we're going to focus purely on the positive square root, the one using that classic radical symbol.
Remember our magic trick where adding consecutive odd numbers builds a square? Well, we can use that exact same logic to find square roots through repeated subtraction. Let's take 81. We subtract 1, then 3, then 5, then 7, and so on. We just keep subtracting consecutive odd numbers until we hit 0. For 81, we hit 0 exactly on the 9th step. Because it took 9 steps, we have proven mathematically that the square root of 81 is 9. Sure, it's kind of slow for massive numbers, but it beautifully visualizes exactly how squares are constructed in the first place.
All right, it is time to level up to the next dimension with Section 4, Exploring Perfect Cubes. If a square is a flat 2D grid, a cube is a literal tangible 3D block. To get a perfect cube mathematically, you just multiply a number by itself 3 times. So, n times n times n. Picture a large cube built out of smaller wooden unit blocks. If it has 4 layers, and each layer is a 4 by 4 flat square, then each layer has 16 blocks. Multiply that by the 4 layers, and you get 64 total unit blocks. Meaning, 4 cubed is 64. Now, what's really interesting about these perfect cubes is how they contrast with squares. Remember how squares could only end in a really limited set of digits? Cubes completely ignore that restriction. 1 cubed is 1, 2 cubed is 8, 3 cubed is 27, all the way down to 10 cubed, which is 1,000. If you look at the units place of all these answers, you're going to see every single digit from 0 to 9 represented. Cubes absolutely can end in 2, 3, 7, and 8, which squares just fundamentally cannot do.
Since that repeated subtraction method would take way too long in 3 dimensions, let's jump into Section 5, Finding Cube Roots Efficiently.
To reliably find cube roots of large numbers, we turn to prime factorization. We break the large number down into its most basic prime building blocks. Let's take 3375. Its prime factors are 3 3s and 3 5s. To find the cube root, we just need to split these factors into exactly 3 identical groups. So we can make 3 groups of 3 times 5. Since 3 times 5 is 15, the cube root of 3375 is 15. It really is that simple. If a number is a perfect cube, its prime factors will always, without fail, split into 3 identical groups.
And now, let's see how all of this builds into our grand finale in Section 6, Figuring It Out Together.
That's right, it is puzzle time. We are treating this like a final boss battle. You now possess every single mathematical tool, rule, and trick you need to crack these questions. I'm going to present the problem, give you a brief second to process it, and then we will break down the answer together. Let's do this. First question. Can you find or at least estimate the cube roots of 27,000, 10,648, and 1331? Take a second to think about it. Use the tricks we talked about. Look at the trailing zeros, and definitely look at those ending digits.
All right, let's reveal them. For 27,000, we know the cube root of 27 is 3. And those 3 trailing zeros mean the root has 1 0, so it's 30. For 10,648, it ends in an 8. From our table earlier, we know only numbers ending in 2 produce a cube ending in 8. A little bit of estimating puts us right at 22. And for 1331, it ends in a 1. Well, 10 cubed is 1,000, so it makes total logical sense that it's the very next number up, which is 11.
Next question. Think of this one as a classic missing piece puzzle. What number will you multiply by 1323 to make it a perfect cube? Remember that prime factorization method we just covered? We need groups of 3. So the crucial point here is exposing the odd factor out. If you prime factorize 1323, you get 3 3s and 2 7s. The 3's are perfectly grouped, but those 7's are incomplete. We have a pair, but for a perfect cube, we absolutely need a trio. Therefore, we just need to multiply by exactly 1 more 7 to complete the 3-group set. So the answer is 7. All right, time for a rapid-fire true or false round to really challenge your memory of our rules. Number 1, the cube of any odd number is even. Number 2, there is no perfect cube that ends with 8. Number 3, the cube of a 2-digit number may be a 3-digit number or have 7 or more digits. And number 4, cube numbers have an odd number of factors. Lock in your guesses.
Well, spoiler alert, every single one of those statements is entirely false. Let's quickly disprove them. 1 is false because an odd times an odd times an odd is always odd. 2 is false because, well, 2 cubed is literally 8. 3 is false because the smallest 2-digit number, 10, cubes to 1,000, which is 4 digits. The largest, 99, cubes to 970,299, which is 6 digits. So it can't be 3, and it definitely can't be 7. And 4 is false. Think back to our locker puzzle. Only perfect squares have an odd number of factors. A cube will only have an odd number of factors if it also happens to be a perfect square number, like 64.
We are going to conclude this explainer today with a final provocative thought. Which of these is greater, 67 cubed minus 66 cubed, or 67 squared minus 66 squared? Don't even try doing the math. Just visualize it. Think about the difference in area between 2 flat squares versus the difference in volume between 2 massive 3D blocks.
the volume of a cube grows exponentially faster than the area of a square. The difference between those cubes is vastly, infinitely greater. Think about how dimensions alter scale the next time you see numbers out in the real world. Keep learning, keep questioning, and we'll see you in the next explainer.